I think one thing that's been usefully demonstrated over the last 40,000 years or so is that wheels are really useful. And in this example, we have two interlocking gears. And, they're going to have teeth in there, so they hook together. But they're wheels, which means they're circles, which means we can make statements about the area of each circle and the radius of each circle. And that's what I want to focus on in this problem. It's asking us for the number of revolutions made by gear B if gear A makes a single revolution. Okay, so it wants to know if gear A makes one turn, how many turns does gear B make? You can see that B is going to make multiple turns because it's a smaller wheel. And the clue that we're going to use to get through this is the fact that their areas are related by a ratio of 5.8. The area of A is 5.8 times bigger than area B. So let's draw some things on this setup. There is a radius. I'm going to call this radius B. And here's another radius. I'm going to call that radius A. And this circle has an area, which I'm going to call area A. This circle over here has an area, which I'm going to call area B. And now we're going to use our understanding of the area of circles to work our way through this problem. Remember what area is. The area of A, circle A, equals pi times the radius of circle A squared. And the radius, or the area of circle B, is going to be very similar. It's pi times the radius of that circle squared. Well, I'm told here at the very beginning that the wheel A is bigger than wheel B, and its area is greater by a factor of 5.8. So what that means is, if you set up a division like this, the result of that division is 5.8, right? Area A divided by area B equals 5.8. So let's use that. And if you look at the very right side, over here, here's what cancels out. The pi's cancel out, and you just have this. You have RA squared divided by RB squared, and that's equal to 5.8. Now I can rearrange this using the properties of exponentials, which is the radius of wheel A divided by the radius of wheel B squared. Okay, instead of having individual squares on each numerator and denominator, I just pull the squared outside. That's using the quotient rule of exponents. Okay, so now I want to know how the radius of wheel A is related to the radius of wheel B, and if I know that, I can talk about their circumferences. If I know that, I can talk about how many spins one takes compared to the other. So let's take a square root of each side. Watch what I'm going to do here. I'm going to square root this side, and I'm going to square root that side. So what do we get? On the left, I've got the square root of 5.8. Who knows what that is? It's some number. But on the right, the square root takes care of the squared, and you just get this. RA divided by RB. Okay, so I'm going to square root 5.8. I think it's time to do that. Square root of 5.8. Okay, you get 2.41. And what that means is the radius of wheel A is 2.41 times bigger than the radius of wheel B. Now, we need to talk about how many turns get made here. And remember what turns are related to, that's circumference. So I can say something pretty interesting, which is that the radius of wheel A equals over the radius of wheel B is equal to the circumference of wheel A divided by the circumference of wheel B. And how can I do that? Right? You might wonder. Well, circumference is just 2 pi r, right? So I'm talking about 2 pi RA divided by 2 pi RB. See how those 2 pi's cancel out? That's right back where I started. So what I'm talking about here with this 2.41 is really just the ratio of the circumferences, which tells me how many times that smaller wheel is going to spin around. It's going to spin around 2.41 times because it has 2.4 less length. So it needs to spin that many more times to make up the same distance.